Welcome to the session on outlier deduction. Outliers are data points that deviate significantly from the majority of observations. They may represent data entry errors, rare events, or meaningful anomalies. If not handled carefully, outliers can distort statistical summaries, mislead visualizations, and degrade machine learning performance. In this video, we will learn how to detect and handle outliers using visual methods and the interquartile range method step by step using Python. In this session, we begin by creating a sample data set using pandas. We begin by importing the pandas library, which is used for data manipulation and analysis. Next, we create a simple data set. The data set contains two columns, student, which stores student identifiers, and marks, which stores numerical scores. Most of the marks fall within a narrow and realistic range, while one value 300 is intentionally set very high to simulate an abnormal observation. Converting this data into a data frame allows us to inspect and analyze it in a structured way, which forms the foundation for systematic outlier deduction. We first perform a basic visual inspection of the marks column by typing df of marks. By directly observing the values, it becomes evident that one score is far removed from the rest. This initial step is important because exploratory analysis often reveals anomalies even before statistical methods are applied. To strengthen this observation, we then use a box plot as a visual outlier deduction tool. First, we import the matplotlib library for visualization. Import matplotlib.pyplot as plt, plot we use to tell it. Then we create a box plot for the marks column. Plot.boxplot of df of marks. And then we also type the title of the plot as box plot for student marks. Then we also label the y-axis as marks. By only giving plot.show, the picture is visible for us. In the box plot, the box represents the interquartile range. The line inside the box represents the median. And individual points beyond the whiskers is the dotted line, represents outliers. Here, the value 300 appears clearly outside the normal range, confirming it as an outlier. After a visual confirmation, we move to a statistical approach using the interquartile range or IQR method, which is widely regarded as a robust technique for outlier deduction. The interquartile range or IQR method is one of the most reliable techniques for outlier deduction. We calculate the first and third quartiles of the marks column by typing df of marks dot quantile of 0.25 is stored in Q1 and df of marks dot quantile of 0.75 is stored in Q3, where Q1 represents the value below which 25% of observations fall and Q3 represents the value below which 75% of the observation falls. Here 25 and 75 are percentiles. Percentile tells the position below and above how much percentage remains. The interquartile range is the difference between Q3 and Q1. Hence we type IQR is equal to Q3 minus Q1. The IQR measures the spread of the middle 50% of the data and is resistant to extreme values. Using the IQR, we define the acceptable range of values. Now we type and execute. Lower limit is equal to Q1 minus 1.5 into IQR and the upper limit is equal to Q3 plus 1.5 into IQR. Any value falling below the lower limit or above the upper limit is considered an outlier. We now filter the dataset to isolate the outlier. DF of DF marks less than lower limit or DF of marks greater than upper limit is stored in outliers. This condition selects all values that lie outside the permissible range. Output shows that the student with marks 300 is identified as the outlier. In some cases, outliers may need to be removed before modeling. We create a clean dataset by keeping only the values within the acceptable limit. DF of DF marks greater than and equal to lower limit and DF of marks less than and equal to upper limit is stored in DF of clean. This step removes the extreme value while preserving the rest of the data. It is important to note that outlier removal should always be guided by domain knowledge. Finally, we compare the dataset before and after removing the outlier to highlight its impact. The comparison shows how a single extreme value can significantly influence the overall data distribution. Once removed, the remaining marks form a consistent and realistic pattern, better suited for further analysis or modeling. This example illustrates that outlier reduction is not about blindly deleting data but about understanding anomalies and making informed decisions that preserve the integrity and reliability of analytical outcomes.